This is the first video on section 4.2, limits of vector functions. And so first of all, let's recall from Calc 1 the epsilon delta definition of limit, and I have it outlined right here. So we have the limit as x approaches c of f of x as L if for all epsilon greater than 0 there's a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus c is less than delta, but also we don't really, we're not interested in what happens when x is c, so we want that absolute value to be greater than 0. Remember that absolute value is how we measure distance in the real line. So here when we say f of x minus the absolute value of f of x minus L is less than epsilon, we're saying these two things are close together. How close are they? They're within epsilon of each other. And how do we get those two things within epsilon of each other? By getting x and c close to each other, but not necessarily equal to. So how do we measure closeness here? With delta. We say if we get x and c this close, but not equal, f of x and L are this close. That's how we measure the distance in the real line. Now, for vector valued functions, we have f from R into Vn. In the notes, I wrote R3 here. So I wrote R3. That should have been V3. So it's not exactly wrong, but is not consistent with the notation I'm using in the course. And so f is a function from R into Vn. And c is an element of R. And we're going to talk about the limit as x approaches c of f of x being a vector L because f is a vector valued function. So this limit is a vector that lives in Vn. Now, just like with limits from Calc 1, back over here, limits and function values aren't necessarily the same thing. So we don't need c to be in the domain of f, and L is not necessarily in the range of f. So what do we mean by this? Well, for all epsilon greater than for all epsilon greater than 0, there is a delta greater than 0, such that the magnitude of f of x minus L is less than epsilon whenever the absolute value of x minus c is less than delta, but greater than 0 because x is not equal to c. This right here is how we measure distance in Vn. We take the magnitude of f of x minus L. That's how we measure the distance between these two vectors. Just like here is how we measure the distance between two numbers. Remember what I said before. You can think of R as V1. So you can think of the real line just as V1. So here we're measuring distance in Vn, and again, this is how we measure distance in R. Now, this may not be good news because perhaps you did not like the epsilon delta definition of limit in Calc 1. But there is some good news here. Let's suppose we define a function in terms of real valued functions. So this seems a little bit strange, but we're going to call x, y, and z real valued functions. They're functions from R into R. And then we're going to define f, I'm jumping a little bit, we're going to define f from R to V3 by f of t is xt, yt, zt. Now, the other assumption is the limit as t approaches c of x of t is alpha, the limit as t approaches c of y of t is beta, and the limit as t approaches c of z of t is gamma. Then, the limit as t approaches c of f of t is alpha, beta, gamma. In other words, all we have to do is calculate the limit of each of these three functions, and if the limit exists, then the limit of our vector valued function also exists. And component-wise, it's just each limit. This is the limit as t approaches c of x, limit as t approaches c of y, the limit as t approaches c of z.